All right, welcome to Module 2.3. This is going to be the first portion of this. There are only two subsets. In this one, we're going to be talking about organic matter. In 2.3.2, we'll be talking about the microorganisms that help make that organic matter. So we talked before about increasing soil carbon. That is going to be directly relation to our improving our soil health. This organic matter is also going to help give us some soil structure and some stability. So the carbon cycle is really just composed of two things. There are two basic processes in this carbon cycle. For the most part, we're going to be mineralizing carbon. So we're going to, basically, this is organic carbon being converted to carbon dioxide. And these microorganisms are responsible for that. So they're going to use the carbon in the soil. That carbon dioxide is then kind of released into the atmosphere. So not only are the plants releasing some carbon, the microorganisms releasing carbon dioxide, humans have an impact as well. But for the most part, when we're discussing plants, we are discussing our soils. We're discussing these two basic processes of the carbon cycle, in that there's photosynthesis and then decomposition. And so if you remember from plant science, the photosynthesis equation is carbon dioxide plus water is going to give us a sugar, and then oxygen and water, mostly oxygen. And then when we have decomposition, when those plants die, they're going to release some of that carbon back into the soil. So the carbon cycle is fairly simple. There's going to be we have carbon dioxide in the atmosphere that plants are then going to pull out, and that's kind of where this climate smart agriculture is coming from. And the more crops that we grow, which we need to grow anyhow, is going to minimize or reduce or decrease the atmospheric carbon dioxide. And so that as these things start to decompose, there's going to be this removal and this addition of carbon dioxide. So for carbon, you're going to hear the term carbon sequestration, and that is just going to be how much we remove from the atmosphere into the soil. And so this is why we kind of want to grow more crops, because our above ground biomass is what takes the carbon dioxide out of the atmosphere. Well, we need to make sure that when they die or they decompose, that we are keeping that carbon inside of the soil, and we are doing that with our living biomass. Our roots and our microorganisms are actually kind of putting that into the soil and holding it there. So a term that you might hear is this term recalcitrant or stable, meaning that it is very difficult to decompose or to break down this particular organic and inorganic carbon. So they're deep in that subsurface environment. So that's kind of what we want to do, is we want to increase that carbon dioxide, decrease the carbon dioxide from the atmosphere and increase the carbon concentration in the soil. And we want to start getting more layers on top of that so that we can kind of essentially bury that carbon dioxide or carbon that we removed from the atmosphere. So some of the organic components of a soil are obviously going to be our residues. Next, we're going to have decomposing organic matter. So this is, the leaf that fell over the winter that is going to decompose in the early parts of the spring. And then by the end of summer, that has now decomposed, because as we increase the temperature, we're increasing microbial populations, and these can be broken down a little bit easier. We have that stable or recalcitrant organic matter that is kind of deep within that. We're not really going to influence this very much because it's already kind of done its thing. It's what's left over. and then the living organisms. And so this is where we get into 2.3.2, in that those living organisms are going to help us create some of these, right? This, especially this decomposing organic matter. And what's important to note is that the soil has this great kind of capacity to hold on to all of this carbon, even more so than all the plant and atmospheric carbon combined. So that's why we're looking to soil health, so that we can improve. We want to improve soil health, because the healthier the soil is, the better it's going to decompose some of these plant materials, the more carbon sequestration we're going to have, where we can kind of hold and store that carbon. And if we don't till our lands, we don't create carbon dioxide, because what happens when you till the land over is you're going to increase the potential or the exposure of that carbon to oxygen. And if you have carbon plus oxygen, you create more carbon dioxide. So by allowing that crop material to pull in that carbon dioxide, when it dies, it's going to have that carbon still in its structure. And if you have those residues, then you're going to continue to improve, or increase this decomposing organic matter that ultimately turns into stable organic matter, right? So that's kind of the thought process of this climate smart agriculture, is to remove the carbon dioxide, make sure that the plants decompose and store that carbon in the soil rather than sending it back into the atmosphere. All right, so we have two fractions, or two different types of soil organic matter. We have the active fraction, and this is going to be, this is going to have a high carbon to nitrogen ratio. About 10 to 30% of our total soil organic matter is going to be in the active fraction. And so this is going to be the most susceptible to soil management practices because it's not very stable. Next, we have the passive fraction. And so this is very stable. This is going to be the actual organic matter, right? This is you'll see in the next couple of slides. This is going to be these large structures that have been synthesized over time, and they're very, can be difficult to break down. So the active fraction is going to be like your leaf material or your plant material. This is going to be food for those soil microorganisms. The passive fraction, nothing's really kind of messing with that anymore, or decomposing or creating that, because it's already created. But we need this because it's going to improve our cation exchange capacity and our water holding capacity. So we need to have both. But we also want to increase our passive soil organic matter, because this is going to give us kind of this, when I talked about pH-dependent charge, that organic matter, when you change the pH, is going to help improve the size of the cup of your land. All right, so for the decomposition process, having an understanding that plants are mostly water and the rest is 25% dry matter, and it is that dry matter that ends up being decomposed and turns into the passive fraction. So we have different compounds that make up our plant. We have cellulose, lignins, proteins, fats, waxes, and polyphenols. If you get into really kind of soil organic matter, we can see we have these bicyclic compounds. If you have to take organic chemistry, don't go ahead and change majors now. It's not fun unless you're into that kind of stuff. But understanding that to break these bonds requires a lot of energy. And so that as we start to increase the amount of these phenolic rings and these bicyclic compounds, we're going to, this is going to be very difficult to break down, lignin especially. So, and we'll see this throughout, that the smaller the compound or the less complicated or complex the compound, the easier it is to break these bonds and then decompose that material. All right, so for our rates of decomposition, and this makes sense when it comes to, I use this as like human digestion as well. So like if you were hungry and you needed a boost of energy, you would probably eat a Snickers bar, right? Or you would look for something that has some sort of sugar, maybe a starch, some carbohydrate, or a simple protein that you can gain some energy from. And that's going to break down very quickly. If you wanted to eat a meal that is going to last you the rest of the day, you would want to eat a meal that is high in fats, carbohydrates, and oils, because that's going to be the energy. It's going to take a long time to break down that fat. And then our lignin and phenolic compounds. And so lignin is really just like the structure that doesn't really get broken down very easily. So if you have ever seen like a corn plant that is decomposed or decomposing, it's going to take a while for that corn stalk to decompose because there's a lot of lignin there. And that is not easily broken down, as we can see here. This organic, this molecule with all of these phenolic rings is very difficult. Those bonds are strong and they cannot be broken down very easily. They require more energy, and we actually use the fungi to decompose these because they like this particular, they have the ability to break these bonds. This doesn't do anything for them. So the rate of decomposition going from fast to slow are going to be the things that are easiest to break down. C6H12O6 is very easy to break apart. We use that as energy, and then we look for more sugars. Our fats and waxes, and then our lignins, these are going to be more difficult to break down, and they're going to take a longer time, and we need to add some things to that so that we can increase the decomposition of these particular compounds. All right, some things that are going to influence the decomposition are primarily going to be how much oxygen is available. And so when there's a lot of oxygen available, things can get decomposed very quickly. And you just have to think about that. If you were to put a leaf in a jar with very little oxygen, would it break down very easily? If you had the right type of anaerobic organisms to break that leaf down, then no, it would not. And so we want to have an aerobic system, exposure to oxygen, and also organisms that are exposed to oxygen to be able to decompose that very quickly. They're also going to need these, at least these three main elements, just like our plants do, in order to break that down. They need the energy as well. Not so much that you need to know all this, but just to understand that, we're going to break these proteins down into these different components. We're specifically going to look at this one in Module 3 when we go over the nitrogen cycle. But just to kind of walk you through that, we have this organic molecule. We need oxygen, and that is going to form carbon dioxide and water and some energy. And so here, anaerobic decomposition is just going to be much slower, and that's why it takes a while for methane. Anaerobic decomposition is much slower, and the byproducts of that are methane, so no oxygen. So instead of CO2, we have CH4. Methane is a greenhouse gas, and it doesn't break down very well. All right, so we have two different classes of organisms. We have autochthonous, and this is going to digest that very resistant or stable organic matter. These are going to be our fungi. And so when we went back to the lignin with that large molecule that's very difficult to break down, our autochthonous organisms are going to be the ones that do that. We have zymogenous organisms, And these are the ones that break down the sugars and the simple proteins. They have a lot of activity, and they're in large quantities as well, because we need to break down that particular, that first part of that leaf material and get some of those out the way. Once we break those down, we can continue on down that list. So autochthonous and zymogenous. The things that are going to influence the rate of the decomposition. So the things that we talked about before are just factors, but the rate of the decomposition is going to be dependent upon primarily environmental conditions. And this goes all the way back almost to like the very first module that we ever went over, or maybe the second one that we went, where I talked about that as the temperature increases every 10 degrees Celsius, we get a 2x increase in the bioactivity, in the biochemical reaction rate. So the hotter the temperature, the more rainfall that we have, we're going to see greater organic matter. Within that, these environmental conditions, here's our pH, here's our moisture, and our temperatures. And so these are mostly geared towards making sure that the microorganisms have a good environment with a lot of energy in the water and the temperature that they need in order to decompose this material. And so for me, when I'm thinking about these environmental conditions, this pH, I want you to think about which environment would you be most productive in? Would you be most productive in a place that had no moisture and the temperature was 0 degrees Celsius, where it's freezing? How active would you be? Not very much, right? I don't like the cold. When it's cold, I'm not doing anything. I mean, it's almost impossible to get me to go outside. That's what I like about plant science. When it's cold, plants don't grow. All right. We'll see you tomorrow then. So that's kind of these, when I think about that, the environmental conditions, we're really doing this for the microbes. And so we want these conditions in order to improve the decomposition or the decomposition rate. Next, we have the quality of the residues. And so is this, does this have a high carbon to nitrogen ratio? Some of the physical factors are going to play a role as well. And then the quality of these residues are going to be what we talked about earlier. What are the components of that plant material? So decomposition rates, environmental conditions, quality of the residues, these physical factors, and carbon to nitrogen ratio. So when we talk about the quality of the residues, if you have a lot of sugars and starches in that, the decomposition will be fast. If you have a lot of lignin in those residues, the decomposition will be slow. So what are those residues made up of primarily? Next, the physical factors are going to be the location and the particle size. And so, if the plant, or let's think about leaf material, right? Let's say that you raked up all of your leaves and you just kind of put them in a pile on top of the soil, and they weren't really exposed to any of these microorganisms. Well, then they probably wouldn't break down as much. If these were in the soil, they would break down a little bit quicker, because we have earthworms and microorganisms and fungi that are going to break that down. Next, we have the particle size. And so if you have a whole leaf versus if you ran that leaf through a shredder, which one do you think would break down quicker? The whole leaf or the one that's been shredded? Well, the one that's been shredded, right? Because it has a smaller size. And the greater the surface area means that more organisms can now begin breaking that down. And also that's going to break up some of these lignins and these waxy coatings that's going to allow those microorganisms to kind of get into that leaf material and begin the decomposition process. This one is huge. This one is probably what I would consider one of the most important factors for the rate of decomposition. And it really has to do with how much carbon is there and the amount of energy needed in order to break that carbon down. So microbes need about 24 grams of carbon to 1 gram of nitrogen. So, that C/N ratio is going to be somewhere between 24, 25 to 1. These are going to vary. They're not going to be perfectly exact, but just think that somewhere in the range between 24, 25 is kind of like net. It's just that's the middle range. Anything on one side of the other is going to either result in net mineralization or immobilization. And so that as we increase the carbon to nitrogen ratio, our nitrogen in the soil is not available to the microbes. It's not available to the plant because the microbes need it. So if we have plants that decompose very quickly, that nitrogen will be released into the soil. So here we are with our ideal microbial diet, and anything below this is likely to result in a net mineralization, or we're going to get a nitrogen credit. And it is we have legumes, we have our vetch cover crops. Applying these are very, you got to think about like alfalfa compared to, rye. Alfalfa is a very succulent, soft plant. It's going to decompose very quickly. Those minerals are going to be released easily into the soil. And that's also why we kind of like to feed alfalfa, because we're going to get that quick release of those minerals. Now, up here for our rye and our wheat straw, as we went back to our mulches and we talked about that we want to, maybe put something over our soil that is going to minimize the impact of that rainfall. We would not want to put hairy vetch over that soil because it's going to decompose very quickly and we have to come back and redo that. So we put wheat straw down because it's going to take the microorganisms a considerably longer time to decompose that material. And so if any of your grandparents have a garden and maybe they kind of raked up the leaves and they put those in the garden and then they would maybe add some manure on top of that, that is giving those microbes that nitrogen that they need in order to decompose that high carbon to nitrogen ratio material. When that material breaks down, it is going to form humus. And that humus is what is going to hold the water and the nutrients. That is this big molecule that, and we go back to soil colloid chemistry where I talked about pH dependent charge, those functional groups of organic matter. That is where we're getting this from. This humus is those functional groups of that organic matter. This is also, gives us some buffering effect against pesticides because it has both those positive and those negative charges. And it can also make our soils a little bit darker. So if you see a dark soil, you are likely to have a lot of organic matter. Oh, and right here, this one, establish and maintain soil structure to reduce soil erosion. Two big ones right there. So here we are back again with this total organic carbon that gives us our soil health properties. Remember that living and dynamic component of that soil is what we consider to be soil health, chemical, biological, and physical. All of these things together are tied into this organic carbon or our organic matter. So there are different components to organic matter. We have non-humic substances, which we're not really too concerned with, but we are concerned with these humic substances. And in the next slides, we'll talk about these three different components and how, and kind of what role they play in our soil organic matter. So all of these things are going to end up being decomposed. We have our biomass. We have like a corn stalk that we are starting to see become degraded or decomposed. And then eventually we get down to this point to where we can't really tell what that structure was. So this is like humus is the complete breakdown of all of those tissues that form into our humic structure, humic substances. So one of the first ones that we have is fulvic acid. And fulvic acid has the lowest molecular weight. This structure doesn't have too many of these phenolic rings. It does have a couple of double bonds, so mostly carbon, oxygen, and hydrogen. The lowest molecular weight, and therefore it is the most susceptible to microbial attack. This would be the first thing you would want to break down as a microbe because it's easy to break down. Next, we have humic acid. And so as the molecular weight increases, the resistance to microbial attack increases. Notice the difference in how many phenolic rings there are now here compared to this molecule. So as the molecular weight increases, we're going to increase our resistance to microbial attack. And so this is ultimately kind of the progression from plant leaf, corn crop stalk to a fulvic acid into a humic acid, and then finally into humin, Humin. And look at this structure. There are so many bonds and phenolic rings, and these are hard bonds to break, and so it's very resistant to microbial attack. All right, we'll take a little break here. This will end module 2.3.1, the first half of it. I'll finish up the second half of it just to kind of chop that time up and make about 25 or 35 minute videos. All right. All right, so starting the next portion of module 2.3.1.